So in order to start this, I want to start with 3 motivating examples. In order of complexity. And some of these examples I will give you a lot of details because I will use them recurrently in order to illustrate many of the techniques that they will introduce. So the first example is the 80 ODE, the 80 ordinary differential equation, and the associated series that you find when you solve this ordinary differential equation. So this equation is very elementary. It's a second order linear ODE. And you cannot really solve this equation in closed form by using elementary functions. So one thing that you can do in order to solve this is to introduce a formal power series, which is valid when x is very large. Okay? So when x is very large, you can try to solve this equation via one of these divergent formal power series that are the natural array of resurgence. So I'm not going to give you all the details, also this could be a kind of good exercise. So let me actually write this formal power series first, because as I said, we are going to use it very often in examples. So there are actually 2 of them. So I'm going to call them phi 1, 2 of z. And let me already point out that in these talks, all formal power series are going to be denoted by phi of z. And this is the series, which I'm going to write in all its glory detail. So this is the aspect it has. So these are the coefficients. And there is going to be phi 1, where the actually let me invert the sign, plus minus. Phi 1 will have a minus sign here, and phi 2 will be the same thing, but with a plus sign. So you actually write down what this is. We find that this is 1 plus minus plus 5 over 48z. Now this series, actually you can see that it's actually divergent. It's factorially divergent because you see here an, you have something that grows exponentially, and then you have here 2 gammas, which go like n factorial, and 1 n factorial divided. So essentially an grows like n factorial, and this formal power series have 0 radius of convergence. However, they are useful in understanding solutions to this ordinary differential equation. So out of this formal power series, you can construct two formal power series with exponential. So let me do like this. X and then you get you have phi 1 over 2, we start with x minus 3. So these functions, so these formal functions are given by this formal power series multiplied by some exponentials and with a prefactor. And you can actually see that these formal functions, I call it formal functions because they are not really functions, because this is not really a function. But this formal expression, actually, these 2 formal functions actually solve this equation as a power series in x to the minus 3 powers. Okay, so this is an expansion which is valid when x is very large. And of course, if this is not a real function, you can try to understand what's the meaning of this. What is the meaning of this expression? Well, it turns out that this equation has 2 actual solutions, 2 linear, I mean, this is a second order differential equation, so it has 2 actual linear independent solutions, which are sometimes called AI of x and BI of x. So these are actual functions. And you can see, for example, one thing that you can say is that these expressions give you asymptotic expansion for these functions. So for example, if x is positive and large, you can actually approximate this function I of x by this formal function phi I of x. But already this statement is highly non-trivial. What does it mean that we are approximating this function by this formal expression? Well, essentially, there are many ways of making sense of this, and actually making sense of this as precise as possible is another of the goals of Resurgence. But essentially, so this is what we call an asymptotic expansion, and morally, what this means is the following. It means that if x is sufficiently large, you can get a very good approximation of this function by appropriately truncating this formal power series. So this formal power series, of course, doesn't make any sense, but if you truncate it, you have something that makes sense. And what this asymptotic expansion means is that if x is sufficiently large, you can always truncate this expression optimally in such a way that you get very good approximation for x. And the optimality of the truncation depends on the value of x. If x is very large, you can truncate this relatively very far. If x starts like getting less and less big, you will have to truncate this much earlier. And one important thing is that you will never get an exact statement after this expression. You will never be able to reconstruct exactly the full function from this approximate formal power series after a truncation, because truncating means that you are actually going to get rid of some of the terms. And actually, another of the goals of this lecture is to show you how to actually convert this approximate or asymptotic statement into an exact statement. And this will be another of the gifts that we will get from this theory of result. Okay. So this is an example, but of course, this is an example that reappears in different forms in many examples, because every time you have this ordinary differential equation that you cannot solve explicitly, you might try to solve it in asymptotic form near, for example, in the linear case, near what is called an irregular singular point. And you will generically produce solutions which are formal power series which are divergent, because the coefficient of factor. So it's important, if you really want to understand how to solve ordinary differential equations with this technique, to know exactly what's the meaning of these formal power series. Okay, so this is an example that appears already in the context of basic mathematics. So let me now pass to another more physical example. Because when we think about perturbation theory, you think very often about problems in quantum theory. Of course, you can also do perturbation theory in classical physics, but I want to now give you an example of perturbation theory in quantum mechanics. Okay.
At least you've muted yourself.
In much detail, because I will come back to these AV functions recurrently during these lectures to illustrate the aspects of this theory of resurgence. So quantum mechanics is one of the kind of favorite arenas in which you have to use perturbation theory. And this already happens at a very elementary level. Right? So this is actually an exercise that many of our undergraduate students do, which is the following. So let's work in one dimension. So let's consider a Hamiltonian, quantum Hamiltonian, which is given by this. So here, X and P are Heisenberg operators. They commute to IH bar. Okay? So this is one of the Hamiltonians that we actually give to our undergraduates. And you see here, G is a positive real number. Now, notice that if G is 0, this Hamiltonian P squared plus X squared over 2 is the Hamiltonian of the harmonic oscillator. Okay? So essentially, you have this sort of Hamiltonian here. So you have so this is the kinetic term. So this is the potential. So this is a quadratic potential. And this is, when G is equal to 0, this Hamiltonian is one of the canonical solvable models in quantum mechanics. And in particular, we know that this Hamiltonian, the Hamiltonian of the harmonic oscillator, has an infinite number of eigenvalues. We know, for example, that the ground state energy of this harmonic oscillator, if you let me use units in which h bar is equal to 1, is just 1/2. Okay? But what happens when you introduce this additional coupling G, when you perturb this solvable problem with this term here? Now, this problem is no longer exactly solvable. So what you can try to do is to try to write the physical quantities that you want to compute in a formal power series in G. So you assume that G is non-zero, but it's very tiny, so you can try to construct a solution of the problem as a formal power series in G. And as I said, this is one of the things that the students in third year of physics learn to solve. And you can actually calculate this systematically. This is one of the things that they learn. And you can actually produce a formal power series in G. So this would be the first term in this formal power series. And now, the question that you can ask yourself is the following: how this formal solution as a formal power series in G compares to the actual answer? We know that if you have what is called a quartic oscillator, an harmonic oscillator with a quartic perturbation, we know that this is a case in which we have a potential which is confined. So a classical particle in this potential cannot actually go away. So this is a confining potential. We know, I mean, it's actually a rigorous result in quantum mechanics that if G is positive, then H has a discrete non-degenerate spectrum. This you can find in books like, for example, the book by Shubin and what's his name? And Veresing. The book by Veresing and Shubin has a very good reference for this. So you can show, for example, that H minus 1 is compact and positive operator. So, and then the spectrum of this Hamiltonian will be functions A0 of G, functions of G that you can order. So you have an infinite discrete number of functions of G, and these are well-defined functions for G positive. Okay, and when G goes to 0, you recover, for example, for E0 of G, you will recover 1/2, and for the higher energies, you will recover the spectrum of the harmonic oscillator. But what you find from this perturbation theory is a power series like this. So let me actually, so perturbation theory gives you an asymptotic expansion. And it was a very interesting question for physicists for many years. What is the nature of this series? This series could be convergent, could be a finite radius of convergence, could be divergent. So the result that emerged, actually not so long ago in the 70s, is that this series is, as the series I was writing for the Dirichlet function, factorially divergent. So the AMs grow factorially, and this means again that this power series is formal, has 0 radius of convergence. So the question arises again: how would you recover this well-defined function of G, which is guaranteed to exist to you by a spectral theory, from this formal power series that appears in quantum mechanics? Okay, so that's another question that you could ask yourself. Again, you could use this philosophy of optimal truncation. You could say, well, if G is very small, I could try to get an approximate value of this ground state energy by optimally truncating the series, so by keeping a finite number of terms in this series. And this actually gives you very good results. But the question is, can we actually make this asymptotic expansion into an exact statement, as we were also asking before for the function? Again, this is the type of question that you would like to answer. And this is the type of question that the theory of resurgence helps you to answer. So this is my second example. So you see it's already relatively more complicated in the context of quantum mechanics. My third example, I'm not going to deal with this in detail, but of course, you can also do perturbation theory in quantum field theory. So what to understand, I mean, I'm not going to give you all the details here because this is really becomes much more complicated. But let me actually, to motivate how things go in quantum theory, let me actually come back to my example of the A function. Now, so if you come back to the A ordinary differential equation, one thing that you can see very easily is that although it doesn't allow solutions in terms of elementary function, you can write a solution in terms of an integral expression. So it turns out that this expression so this integral form for the solution actually solves this ordinary differential equation. So you can actually choose paths of integration for this integral, which makes this function to be well defined, which makes this integral well defined. Okay? And it's not very hard to see that there are two independent paths that give you two different solutions to this equation, which eventually are going to be the A function I and the A function B that I was writing before. But now you can ask yourself, how would you obtain the actual, the asymptotic expansion that we were writing down, starting from this integral? And the answer, so the answer is that you can use what is called the saddle point method to actually do this. So let me just give you a kind of short answer. And if you look at the, I can actually formulate this as an exercise for you. And if you look at my notes, you will see the kind of details of this exercise. So in the saddle point method, you actually look at critical points of this point that we here. So the critical points here is very easy to see that you get, when you take a derivative with respect to W, you get this equation. So there are two critical points. And you can see that these two critical points, when you expand formally this integral on these two critical points, you will recover the two exponential solutions that I was writing before. So you can see that if I expand this integral around these two critical points, you will get actually this behavior that we were finding before. And if you now push your saddle point calculation by calculating higher order corrections to the critical point by doing essentially Gaussian perturbation around this critical point, you will actually reconstruct the whole power series that I was showing you before. So essentially, if you have an integral representation of a function, it's very often the case that you can actually produce such as an asymptotic expansions by using the saddle point method. Now, why is this relevant? Remember that I was supposed to be telling you about perturbation theory in quantum theory. Well, this is relevant because in many quantities in quantum field theory can be represented by what we call path integrals or functional integrals. So you have some, I mean, here I'm not going to, of course, enter into the details, but I want you at least to transmit the kind of heuristics behind this. So In quantum field theory, typically have to deal with things like this. So you have a functional or action of a field, where x here is a point in space-time, and h bar appears typically as a parameter that divides s in the exponent of the action, and then you have to do some sort of functional integral, which is not well defined mathematically, over all these field configurations. You see that this doesn't look so different from a simple-minded one-dimensional integral, and in fact, in quantum field theory, what we do is to, in order to make sense of this, at least at a formal level, one thing that we also learn to do is to produce asymptotic expansions. Starting from these formal path integral expressions by doing a sudden point approximation. So you look at field configurations which are critical points of this action. So that they satisfy this equation, and this actually is the classical equation of motion of your underlying classical theory. And then we do something very similar to what you would do here. We do some sort of formal expansion around this critical point. And what you get is a formal power series in h bar, which is an asymptotic representation of the quantity that you want to calculate. So, so in the same way that we would like to make sense of these asymptotic expansions that appear in the context of ordinary differential equations, in the context of Rayleigh functions, we would like to make sense as well of the formal power series that appear in quantum field theory. And this procedure of producing systematically perturbative series from this path integral is something that physicists learn to do. And the question is, once you get these perturbative series, which are going to be asymptotic, how you would make sense of them, okay? But you see, what I want to transmit with this is that the problem is not so different from the problem that you find in more elementary context, okay? So these are the kind of the three motivating problems. Yes?
May I ask you, but in the end, in the quantum mechanics and in quantum field theory, you say it presents itself as similar problems, but in the end, is there some qualitative difference between the power series that you're getting, or?
Actually, surprisingly, they are not so different. This is, I'm now going to introduce, for example, my main technical tool, which is the Borel transform. And the Borel transform is going to have a singularity structure, which will determine many important properties of this construction. And what is quite surprising is that the singularity structure of the Borel transforms seem to be very, very similar from elementary examples, like the Rayleigh functions, to very complicated examples appearing in quantum field theory. So, and this is one of the keys to actually, for the success of this program, that the type of singularities that we will find are not that different at each level. So that's a very good question, but the answer is that empirically we don't seem to find in kind of standard quantum field theory models, including non-trivial models like asymptotically free theories and so on, we don't seem to find a completely different world from what you find in ordinary differential equations, for example. And this is, I think, one of the reasons why this language can be really unifying. If I have time, so this is in a sense the motivation for my lectures. So let me now try to give you some sort of plan for them. So the plan, so this is the introduction. So I'm going to start with what I call elementary resurgent technology. So we'll try to see what are the ways of making sense of all these quantities. And then I will discuss two examples. One is resurgence in the WTB method. And if time permits, which we'll see how it goes, I would like to talk a little bit about resurgence in quantum topology. This already will touch on non-trivial quantum field theories like Chern-Simons theory, which are definitely more complicated at first glance than this ordinary differential equation. Okay? So, but the first thing I want to do is to actually try to teach you some elementary Resurgent technology. So let's see. Let's get to work with this. So I don't know if there are any questions. Is readable what I write here, or? Okay, so let's start then with elementary Resurgent technology. We see this is actually quite simple. So, so my starting point will be a formal power series of this form. Okay. So again, this has to be, this doesn't have to be thought as a function, but as a collection of coefficients. And I write as a formal coefficient. In particular, this might have zero radius of convergence. And actually, I'm going to deal with series in which an grows factorial. Okay? So this is the typical situation for all the examples I mentioned before. Also, I didn't mention concrete examples. In quantum field theory, it turns out that in all realistic examples, with almost all realistic examples, these coefficients grow like n factorial. There's a small generalization, which is the WKB method, in which the coefficients grow like 2n factorial. Okay? But this is not, this is really doesn't involve a big change of the theory, because you can think just that, for example, all odd terms here vanish, and then all even terms are non-zero, and then the even terms will grow like 2n factorial. So you can think about this as a particular case of the case I'm going to tell you now. Okay? Now, so actually, I'm not a very formal person, but you can define the kind of formal power series that you can define so what we want to keep is this character that they grow factorially, and formal power series, which are of the type, are called Gevrey 1. So we say that the formal power series I of z is Gevrey 1 if the ANs can be measured by a factorial times an exponential. Okay? So these are things which grow like n factorial. If you want the subleading growth of the factorial is an exponential growth. And this is going to be very crucial for us. So we see that it's yes.
Does it exist with other numbers?
I think, yeah, I think the Gevrey 2 would be, for example, 2n factorial, Gevrey 3, and so on. Yeah. So the 1 refers to the fact that this is just 1n factorial, not 2n factorial, or 5n factorial. Okay, so now what we want to do is to actually try to make sense of this formal power series. And as we know, the main problem for this power series to be well defined is its factorial growth, which makes the radius of convergence to be 0. So the actual solution to this problem is very silly if you think about it. What we do is to introduce a transform, which is going to be called Borel transform, which is like a radical surgical cure to this problem. So the Borel transform is a map in which you start with a formal power series and you produce, in principle, another formal power series. I'm going to write it with a different argument. And this formal power series is actually defined by taking an and just divided by n factorial. Okay? So this is a very simple operation in which you surgically cut this n factorial growth. But since my series is of everyone type, once you cut the n factorial growth, what remains is exponential growth. But exponential growth is very good because it means finite range of convergence. So a result that follows from this is that this Borel transform is analytically variable. And that's the crucial aspect of this game, because once we are working with locally analytic functions, we have all the complex analysis that comes to our rescue. And you see, this sounds very silly, but we have passed from a world that we don't really control, which is the world of divergent formal power series, to a world of local analytic functions, and this makes all the difference. So let me actually give you some examples of this, because one thing that, when you work on Resurgence, one thing that is very important is to understand how the shape of this formal power series gets translated into the shape of this analytic function. And this will be very important in reading in this game. This can be actually very much clarified by looking at interesting examples. So let me give you a very simple example. Let's suppose you have a formal power series which grows like a gamma, so k minus 1 factorial, and then it has some exponential growth given by a, where a is a real number in this case, and then we have the top. Okay. So this is something that, according to the Borel definition, it has a leading factorial behavior, and then it has a subleading 1 over a exponential growth behavior. So it's a trivial exercise to actually calculate the Borel transform of this. And then you see that when you divide by k factorial, you get 1 over k, then you get a minus k, and then you get z of minus k. And this is precisely this you can actually sum. This is minus log of 1, sorry, this was zeta, 1 minus zeta of a. Okay. So you see that we started with a function with formal power series, which is divergent, and now we get a function which actually is analytic at the origin, and not only is analytic at the origin, it has a finite range, it has a finite range of convergence, which, for example, if a is positive, let me write it like this. Let's assume that a is a real number. Let's suppose that it's positive. And then what we'll see is that we have a region of convergence near the origin, and then we'll find a singularity. So now we have something which is a formal power series which has a finite range of convergence, but you will have a singularity here, and in this case, you will have a logarithmic branch cut. Okay? So this type of behavior in the formal power series leads to a singularity, logarithmic singularity in the Borel transform. And we can actually, let me give you an exercise. Let me write it here. It's also solved in the notes that I wrote. So this is a very small modification of this. So now you look at so you see now you have a factorial divergence, but this is slightly different here. E is a real number between 0 and 1, and you can see by doing this calculation that now the Borel transform will have, again, a near singularity at zeta equal to a, and now it's going to be a branch cut singularity, okay, determined by this parameter b. Okay, okay, so so what do you do once you have this Borel transform? So the idea now, yes.
Sorry, you're saying it will be a branch cut, but your log already has some branch cut.
Yeah. Sure. This is a log branch cut singularity, and this is like a sort of exponential power of singularity. Yeah. They are both branch cuts. Yeah. You could have poles as well, yeah? But in these examples you have branch cut singularities. Now, the next idea in the theory of resurgence is to actually try to understand how these Borel transforms can be defined globally. Now we have, we know that they are analytic at the origin, and we would like to understand if it's possible to analytically continue away from the region where they are, from the neighborhood of the origin which they are analytic. And here comes the idea of a resurgent function, which I'm going to state in some sort of vague terms. Probably, if you ask somebody else to give a course on this, it will get more precise. But the idea of a resurgent function is that these Borel transforms can be analytically continued away from the domain of convergence, and you are not going to find a very Ostrowski set of singularities. Okay? So essentially, you can find an infinite number of singularities, but these singularities, even if they are infinite number, can be avoided by appropriate paths. So the idea of resurgent function is that on any line issued from the origin, so this is the definition that you find sometimes. Yes.
A line or a ray?
No, not a ray. It doesn't have to be. It's actually any line or any line of finite length, and not. It's not a ray of infinite length. So on any line with a given length, there is only. So this is of finite length.
But not a straight line.
Not necessarily straight. Yeah. Let's say on any of finite length. There is only a finite number of singularities. This is a vague definition by rigorous standards. But since I'm more like an explorator than an administrator, it's sufficient for me. So, these are a finite number of singularities, and you can actually such that I have to continue here. This function, this Borel transform, can be analytically continued. Maybe can be analytically continued. Along any path that follows it along any path that follows the line by circumverting the singularities. So this so what does this mean? Well, let's suppose that we are in this situation that we were writing before. So we have here a singularity, here, for example, in this case. Now, it's clear that, along any line that doesn't cross the singularity, we don't have any problem of doing this analytic continuation. Now, if you take a line which includes the singularity, you can always deform your contour, can always do analytic continuation above or below the singularity. Okay? So in order to do that, you have to avoid the branch cut of the logarithm, or in this case, you have to avoid the branch cut of this function, but you can always avoid that. Now, you could find, for example, yes?
It may be a stupid question, but the branch cut of a log, that's
yes.
A little bit of my choice.
Yes.
So then what does it, like, how precisely should I formulated, because right, you chose the branch path along the positive real axis.
Yes.
And I chose it like vertically, and then like how do I know for any configuration of those branch paths, or is branch path a part of singularity in your definition or not?
I mean, yeah, you have to make a choice of branch path of the log, right? Yeah, that's clear, right? So, and we will actually make choices of branch path for the log. So, in general, you will have to specify a cover of the complex plane and a multi-seated structure of a Riemann surface in order to make sense of this. That's the case, absolutely. Yeah. So, in order, anytime you have a branch path, you will have to specify this multi-seated structure. Okay. So, but you see, you have an infinite number of singularities. This is still fine because you can always circumvent the singularities in different ways. So essentially, this property, what it says is that the structure of singularities that are going to find is not so complicated that you cannot avoid them by choosing appropriate paths. So in particular, this is also the notion, this is what Ekal calls endlessly continuable, or I don't know, endlessly extendable or something like that. I think it's like this. In examples, in actual examples, in actual systems, you always find this type of structure in which you typically find an infinite number of singularities generically, but they are such that this property is actually respected. So, for example, you might have towers of singularities along the complex plane which go to infinity, but can be always avoided by appropriate points. Okay. And I'm actually going to be even restrict even more my examples here, and I'm going to consider what are called simple resurgent functions. Now, simple resurgent functions have the property that singularities are defined by the property that they are resurgent, and these singularities are either log singularities or poles. Okay? So this formal power series defines a simple resurgent function, but this doesn't. Now, of course, this is a small extension of this, and I will also write results for this sort of small generalization. But in my examples, I will actually focus on logs, on simple resurgent functions with singularity, where the singularities are just logs or poles. Okay, this just makes the discussion easier. And what is remarkable is that in many actual examples in physics and mathematics, you only deal with simple resurgent functions. So this is already big enough a class to actually address many of the samples that we will consider. Okay.
You're allowing products or something? Or
sorry?
You're allowing products?
Products
or with the logs, because if you just have logs, you can take the derivative and then you have an actual function.
Yes. But no, I'm not going to take into account products of logs, just simple logs, yeah. Just a log singularity.
You take the derivative of such a function, then
yes.
you solve the
function. Yeah. Well, it has a pole, right?
Yeah, with pole.
Yeah. Absolutely. Yeah. But logs and poles give you some sort of different behavior, right? Because, I mean, for example, the behavior of the coefficients here is very different. So you can see that you see the behavior of the coefficients when you have a log singularity or a pole singularity are different. And these are the small differences that you have to take into account by this singularity structure. So, okay, so I don't know if I'm supposed to make a pause or yes, at 5 now for 5:50. It's okay, 10 minutes pause? Okay. I don't know if there are questions for the audience.
Okay, so do we make a break?
Yes, let's make a break.